Okay. Hello, everyone. Good morning. I would like to welcome our keynote speaker, Dr. Nathan Evans from the University of Queensland to the Mathematical Psychology School. Nathan got his PhD in mathematical psychology from the University of Newcastle with Professor Scott Brown and Professor Andrew Heathcote. Then he spent 2 years, I think, at the Vanderbilt University and University of Amsterdam with Professor Erik Wachenbachers. But he's now a Decra Fellow at the University of Queensland. Very briefly, I can say his research interest is extending, testing, or applying mathematical models of decision making, especially sequential sampling models. Yeah, okay, Nathan, many thanks again for accepting the invitation. Take it away, Nathan.
Oh, no problem. And thank you for having me. I'll go to screen share now, which is this one. All right. Can everyone see okay?
Yes, great.
Yep, cool. I'll just go, well, actually, forward, back. Yep, that's working. That's all working fine. Yeah, thumbs up, Amir. Yes. I just went, yeah. You can see the movement? Sorry, somebody quickly give me a sign so I know that it's working. Okay. Oh yeah, cool. Just wanted to check to avoid technical difficulties midway through the talk. All right, fantastic. All right, so I am going to introduce sequential sampling models or evidence accumulation models. There are several names for these types of models, as you'll know throughout the talk. Introduce them, talk about some different ways they can be used to perhaps help your research, or if you're a student, why you may want to research into them. And then some potential pitfalls that you can potentially avoid. Please feel free to ask me questions throughout. There'll obviously be times for questions at the end, but I think the most important point is that everyone's understanding content as we go. If I'm going too fast, please tell me to slow down. There's a lot of content I can cover, but a lot of the stuff at the end is kind of frosting on the cake. So we can always, skip that bit to make sure you have a better understanding of things. All right. So to begin with, I always like to start off with kind of my idea of what mathematical psychology is and what modeling is and why we do it. So to me, psychology is mostly about making theories about psychological processes, right? As psychology researchers, we want to understand human psychology, we want to understand the brain, the mind, and we usually do this by making theories about these processes and testing these theories. In mathematical psychology, our main goal is to then formalize these theories. So rather than having explanations of why things occur, we now have formal mathematical models that explain why these things occur. Now, there's definitely no shortage of models in mathematical psychology. There are more models than people. Everyone has their 1 or 2 models, or 3 or 10 that they love. So there are a lot of models, right? And this is not going to be a comprehensive talk, right, that covers all models. Obviously, I'm covering the sequential sampling framework, and even within that, I'll be covering a small number of the models. But in general, this will focus on the sequential sampling models, or as they're also known, evidence accumulation models. Both of these names are commonly used. I've put both in because the title of the talk, sequential sampling models, but by habit, I often use evidence accumulation models. So just so you know that there's 2 names for these things. And if I say evidence accumulation models, I mean the same thing as sequential sampling models. I'm not talking about something crazy and new, right? All right. So, I guess the thing to discuss skip ahead of that. I guess one of the things to discuss to begin with is that these models are often aimed at explaining basic perceptual tasks, right? So although they have been applied to more higher level decisions, often the focus of these models is kind of low level perceptual decision making. Tasks like the following, where hopefully you can see my mouse. where you have to judge whether that you get a whole bunch of dots on the screen and you have to judge whether they seem to be going left or right. And so sometimes you'll have very easy trials like this 40% motion coherence one, where there are a lot of dots moving in one direction. And so it's kind of easy to see, oh, look, the general motion that we're seeing in this task is rightward. And sometimes it's very hard and even impossible when there's no motion coherence, right? And you're trying to judge which way these dots are going and there's no actual coherent motion. Everything's just moving around randomly. So again, these models are often applied to Bayesian perceptual tasks. And this is just one of the models, the diffusion model I'll be explaining here. But this is kind of like the basic framework of how these models operate. And so in this case, you've got two options. You've got option 1 and option 2. And this here, this kind of squiggly line is tracking the accumulated evidence for option 1 versus option 2. This dotted line here is kind of like the line of indifference, where the options are equally favored. And this tracks here the evidence over time. So we've got time on the x-axis, and this is your evidence for option 1 versus option 2. So anything above this line is evidence for option 1, and the higher it is, the more evidence it is for option 1. And anything below the line is evidence for option 2. And the further below the line it is, the more evidence there is for option 2. Now there's certain parameters of these models, right? Which tell you what, am I getting chat? Is that for me? Oh, no. How that graphic, sorry. How that graphic, what do you mean, sorry? How is the graph accumulated? Feel free to speak, please. Sorry, no, I'll continue on, then I'll get back to that. Please put more detail in chat, because I wasn't quite sure what you meant there. And so in general, there's the parameters that govern this process, right? So one of them is the drift rate. And this drift rate describes how the accumulation of evidence moves on average over time, right? So this is a very noisy process. As you can see, it's not a straight line. It's all jiggly and stuff's moving around. But the drift rate kind of describes the average rate of movement over time. So if you have a positive drift rate, the evidence is generally moving towards option 1. And if it's negative, it's generally moving towards option 2. So the drift rate governs how you accumulate evidence for the two options over time.
I'm sorry,
yep.
I'm interrupting you. I couldn't understand the options and the information. How did you gather the information? I mean, is this graph for example, EEG or eye tracking movements or something like this? I couldn't understand what are those options.
Excellent question. So the idea is that the evidence is just coming from the sensory information that you're getting from the stimulus. So this is tracking your sensory input. And this process itself is a theoretical part of the model, right? So this isn't actually data. This isn't actually measurements that you're taking. This is how the model itself operates. Now, the model itself only looks at RT and accuracy, which I'll get into soon, but this is purely a dynamic of the model itself. It's not empirical data. This is just how a diffusion process itself works as a model. Does that make sense?
Yeah, I get it. Thank you.
Okay, cool. All right. Please, again, feel free to ask questions when you have them. So one parameter is the drift rate, right? It's this kind of driving force in the model, right? That pushes in one direction. A second is the starting point. So the starting point is the initial amount of evidence you have. So where the process starts when you start making a decision. And in this case, and it represents a priori bias. So bias you may have to one option or another, right? Maybe because of past experience, you prefer option 1 generally to option 2. And so you have some bias towards option 1. But in this case, because it starts on the equal line, it's unbiased. So 2 parameters so far: drift rate, kind of the driving force of the decision-making process, and Z is the starting point. Then we have A, and 0 on the other end. A represents the boundary separation, and these are our thresholds. And our thresholds are what result in us making a decision. So essentially your evidence, you'll be getting sensory information in, and that will kind of accumulate evidence in your mind And then eventually it will hit a threshold, either the threshold for option 1, which is at the top, or the threshold for option 2, which is at the bottom. And that will trigger a, oh yes, sorry, raised hands. Yep, go for it.
Sorry, the evidence accumulation occurs only from the sensory inputs, or can it occur from some higher order processes like pre-assumptions about the situation, or I don't know, tendencies towards one stimuli? Or
good question. So to the most complete and honest answer is these models are quite ambiguous in terms of what exactly constitutes evidence. So really evidence could be any number of things, right? Sensory input, previous experience, practice on tasks, all these kind of things, right? All these things kind of combine into to drive this drift rate, right? So you're perfectly right. It's not just complete sensory evidence that drives this. It's also a whole number of things. I usually just say sensory evidence for simplicity, but the models are quite, what would you call it? But they don't really have a specific. This is what evidence is. They're quite they're vague and non-specific on this. Does that make sense? Agnostic. That's the word I was looking for. Yeah. Yep, that makes sense. Yeah.
Yeah. So the drift rate doesn't represent like signals in the brain, actually, right? Just
I mean, not exactly, but I guess at a higher level. So this is kind of beyond the scope of the talk, but some researchers have shown that if you kind of if you average over many neural firings, then it resembles something that looks like a noisy accumulator. But no, it's not exactly neural firing or anything like that. It's like a representation of a general process that we think is happening. Well, whether this exactly represents neural firing or whatnot, I think is a deeper question that we haven't quite gotten to yet. But think of these models, I guess, a bit more generally than that. Does that make sense?
Yes. So it can be an average from the various signals from different signaling from different part of the brain. Somehow.
Completely right. It's yes. These models aren't specific. They're completely agnostic in terms of what exactly the evidence is or where it's coming from. So yeah, people have linked it to the central parietal area, central parietal positivity. That suggested that's kind of where it's coming from in humans. But again, although there's some evidence to suggest that, nobody really says that that's what's driving these models. So yeah, it's quite agnostic in terms of that. Does that make sense?
Clear enough. Thank you.
All right, cool. Yeah, and so you've got the boundary, and when the evidence hits the boundary, that's when you make a decision for that alternative, and then you'll make it at the time that it hits. So that will give you your response choice. In this case, you responded for option. No, want to go back. Oh, well. In that case, you responded for option 1, and you responded at time wherever this is, wherever it hit along there. And the thresholds can differ, right? So it's thought within these models, it's considered that thresholds are under a human control, right? So you can control your thresholds, and they represent how cautious you are at the task. So if you were to set thresholds like these red ones here, you would not be very cautious at all, right? Because you would require very little evidence for either alternative to make a decision, and you would have decided very early. If you were to have thresholds like the blue ones, you'd be kind of moderately cautious, right? You'd need some evidence, much more evidence than the red thresholds, but not as much evidence as the black thresholds, right? And if you were to adopt the black thresholds, they would be reflecting you being very cautious, right? You need a lot of evidence to make the decision. And so that's something important to keep in mind too. These parameters have meaning, right? So the boundary separation reflects how cautious you are, right? Boundaries that are tighter mean that you're more risky. Boundaries that are more separated mean that you're more cautious. The drift rate, in a sense, is how good you are at the task. So a higher positive drift rate means that you're more clearly accumulating evidence for one alternative, and the top threshold is usually the correct alternative to make it meaningful. So higher drift rate means that you're better at the task. And then starting point, as I said before, reflects a priori response bias. So biases that you take into the decision that may bias you towards one alternative or the other. The last kind of key parameter is something called non-decision time. And in a way, this is kind of a garbage bin of these models. Yes, sorry, go for it.
Could you please tell a little bit about how we could determine the best actually kind of threshold for this task? You know, those blue lines in your last
excellent
page,
question. So determining the best threshold is a matter of what the task goal is. So for example, going back to the previous slides, if you wanted to maximize your accuracy at the task, so be as accurate as possible without caring how long you take to respond to each question, then these black thresholds would be best, right? Potentially even thresholds that are even bigger than the black thresholds, right? Because your goal is to maximize task accuracy. Now, if your goal is to minimize the time spent on the task, then the red thresholds would be best, right? Because you require the least evidence and you'll just respond as quickly as possible, right? Now, if you want to maximize efficiency, so you want to, which I'll talk about later, get the most correct responses possible in the least amount of time, then you want thresholds that are somewhere in between. And there are formulas worked out that can calculate the optimal thresholds. So I guess the key point here is that the best thresholds that you can have will, one, determine on what your goal is, and then two, will be determined by certain properties of the task. But you can always work this out. It's just specific on the context. Does that make sense?
Absolutely, thank you.
All right, cool, no problem. And so the last part of the model is this non-decision time component. And non-decision time is kind of like the garbage bin of response time models. So essentially you have this thing here that's the decision time, and that's what we've been talking about so far. You know, you have this evidence accumulation process till it hits a threshold and a decision is triggered at time t. But then you also have sensory encoding and the motor response that occurs, right? And the time taken to do these things are thought to be, in these models at least, are said to be unrelated to the decision-making process. And they're kind of clumped in together and just called something, oh, didn't have another slide, and are just called non-decision time. So that's the last kind of key parameter of these models. And that's the time that everything that's not the decision process takes, how long everything else takes. And just some quick definitions, because I want to get these out of the way with, so that when I say something, you don't perhaps get confused if it means something else to you. So in this talk, at least, when I say evidence accumulation models or sequential sampling models, I mean models that attempt to explain RT distributions via the evidence accumulation account. The evidence accumulation account being that you get evidence, noisily accumulate evidence over time until you hit a threshold and make a response. So that general account. When I say diffusion models, I mean evidence accumulation models with relative evidence. This is all the Ratcliffe type work, and this is the models that I showed before. When I say relative evidence, I mean that it's option 1 versus option 2, and the evidence for option 1 is also evidence against option 2. Hence why we have opposing boundaries, right? Because if you gain evidence for option 1, you get evidence against option 2. So these are the diffusion models, which are based on relative evidence. The last type of model, evidence accumulation model I'll talk about, are accumulator models. And these are evidence accumulation models with absolute evidence. So these are things like the LBA, LCA, and WALD, if you know them, but you may not. And these are essentially represented by separate accumulators for each response alternative. So again, you have evidence accumulation over time until it hits the thresholds, but you have separate accumulators for response A and response B, and both can be gaining evidence at the same time. So they're no longer dependent on each other. The accumulation is absolute because they're separated. Evidence for option 1 isn't necessarily evidence against option 2. Here's a bigger schematic. I'm not sure if it's helpful, but I put it in just in case. And this is kind of like the layout of how these models work in a way when you're actually using them with data. So you'll have some kind of, so you've got A, B, C, and D. And so in A, you'll have different types of trials, right? And this is a brightness discrimination task. You have to decide whether there's more white or black pixels in the array. So this trial up here is an easy white trial because it's just clearly mostly white pixels. This one here is an easy black trial because it's just clearly mostly black pixels. This one here is a hard white trial because it's mostly white pixels, but it's pretty close. And the same here. This is a hard black trial and it's mostly black pixels, but again, it's pretty close. And then so what happens is that the model will make predictions about what's going on here, right? So in panel B, you have the model noisily accumulating evidence over time for either white or black. In this case, white's correct, so it's in green. In this case, white isn't correct because it's black, so it's in red. And it will accumulate evidence over time and make a decision, right? And these become the predictions of the model. And then in C, as you'll see, if trials are easy, you'll usually have very high accuracy, right? So this is the response time distribution, and you get 99% of the trials are correct and it's shaped like this, and errors 1% are incorrect and it's shaped like that. But in harder trials, you'll have lower accuracy. So it's like 88% correct here and like 12% incorrect here. And then if you move down to D, the process of feeding the models is trying to get the predictions of the models. So as you can see, they make predictions, white, time, etc., to as closely match the data as possible. So again, these are the predictions of the model, and then we have histograms of the data, and then you estimate the parameters by making these parameters most closely match the data as possible, and then these will give you parameter estimates. And as you can see, the estimates are a bit different between hard and easy trials. Hopefully that gives you a basic idea of how evidence accumulation models work. But again, please ask if you have any questions or are confused about anything. However, even with a basic understanding, it may be difficult to know why they may be useful for your work, why these models could help you in your research or be an interesting topic of research. Particularly if you're a student and you're planning to go into research, you may be wondering, well, would these actually make for an interesting research project? Now, my very biased response is obviously yes, but I'm going to try to explain to you in the upcoming slides why these models may be useful for you and helping answering questions that you may want to answer. So I think why evidence accumulation models are useful comes back to a broader question, right? And that's the question of why do we do modeling? What's the purpose for making models? Why are they useful? Why are they important? You know, why have I spent my, career so far doing this stuff, right? And I think there's a lot of possible answers to this, because psychology research is very diverse, right? Even mathematical psychology itself is very diverse. There are a lot of different questions that people are interested in, and a lot of diversity in how they can be answered with models. So I don't think there's any one way to do modeling. I think there are lots of ways to do modeling. And I don't think there's just a single type of question that could be answered with modeling. I think there are many questions that can be answered with modeling. And so I've tried to, in the past, perhaps naively, classify the types of modeling. What are the different ways you can model? This isn't like a be-all and end-all categorization. This isn't necessarily a categorization that you should believe in. This is just a way that makes it easy for me to explain to you why modeling may be useful and what purpose it may serve for you. So my categories are model application, model comparison, model evaluation, and model development. I'll talk about all of these in more detail, but the one that you'll probably want to, I assume most people want to pay most attention to is model application, because I think that's probably what most people want to do with these models. And so I'll also talk about it first. So model application is situations where we want to take an existing model and apply it to some data as a measurement tool. So essentially what we want to do is we have these evidence accumulation models. They've been built previously and tested previously, and we want to take them and apply them to some data to learn something about that data. Hence why they're referred to as measurement tools, right? Because you're not really testing them as theories. You're trying to use them to learn something about your data. And so what people are trying to do here is they're trying to measure some parameters underlying the data, right? So they want to measure the drift rate or the threshold or the starting point or the non-decision time or all of these things, and learn something about their data by measuring these parameters and seeing whether they differ between experimental groups or conditions. And so going back to this schematic before, I had easy trials here and I had hard trials here, right? And as we kind of go through the process, the model makes predictions about it. Here are the distributions of predictions and matching them to the data. At the end, you get to some parameter estimates, right? And they're the closest matching parameters, right? The ones that the model predictions that most closely match the distributions that we see in the data. And as you can see here, the T0, which is non-decision time, those estimates are very close between the two conditions, right? In fact, identical. And the A parameter, the threshold, they're also very close between conditions, in fact, identical. But you get a difference between conditions, between easy and hard trials in drift rate, where drift rate is higher for easy trials than hard trials, indicating that people are better at easy trials than hard trials. Now, obviously, this probably isn't surprising, right? I think everyone would expect, yeah, of course, easy trials would be easier than harder trials. People would perform better at them. But this principle can be widely applied, right? You can estimate parameters for a whole heap of different potential manipulations or conditions and see whether people's task ability or response caution or a priori bias or time dedicated to motor and sensory encoding, whether these differ between conditions or groups. And I think this has a lot of potential applications. And so one example of model application, evidence accumulation models, this will mostly be stuff from my own work because obviously I know it best and therefore I can hopefully explain it better to everyone. So these models have been successful for a long time, right? They're older than me. They're older than my parents. They've been around since, you know, the 70s. So they're very old, right? Or even older if you want to go back to Stone in 1960. However, recent researchers question the validity of these models, mostly through something called selective influence tests, which I'll explain to you now before you ask. So this idea of selective influence tests is quite popular within cognitive psychology. And it's this idea of testing a model by seeing whether a manipulation that you think should only manipulate a certain parameter does only manipulate that parameter. I'll unpack this a bit here though. So the logic of selective influence tests is the following. You've got to be able to implement some experimental manipulation. That's manipulation X. And then you think that this manipulation X, will affect construct Y. So you've got this manipulation and you think it should affect this construct that you think happens as part of the cognitive process. Now you want to validate this model, right, using a selective influence test. And parameter Z of this model, of model 1, is supposed to measure construct Y. So if you want to validate this model using a selective influence test, and you think parameter Z of the model should measure construct Y, and you also think that manipulation X should affect construct Y, then you can have the logic of, well, if the model is valid, then this manipulation X, should only affect parameter Z, because they're both directly measuring construct Y. Does that make sense? Yep. Again, please ask questions if you're having problems or are confused. However, this kind of critically depends on how well the manipulation actually affects what you think it affects, right? How well manipulation X actually affects construct Y. So the most common target of these tests within evidence accumulation models have been speed emphasis manipulations. So people have commonly tried to test evidence accumulation models by implementing speed emphasis instructions, which should make people less cautious, and then seeing whether these instructions result in people lowering their thresholds and only lowering their thresholds. The logic here being that speed emphasis manipulations are supposed to only affect caution, right? If you tell someone to be less cautious, to go faster, they should only become less cautious and not become worse at the task or faster at motor responding, etc. And because thresholds are also supposed to measure caution, so they both map onto the same construct, the logic people have come up with is speed emphasis instruction should selectively affect thresholds, right? But this isn't necessarily the case, I think, right? Telling people to go fast could put them under pressure. Which could make them perform worse due to panic, right? Hopefully you have an idea of this, where if I were to be like, hey, go faster at a task, no, faster, you know, and give you this kind of pressure to keep performing faster, it may put you under some kind of stress, right? And this may cause you to panic and perform worse at a task than you would otherwise. Also, people may see go faster as hit buttons fast, right? So it could result in them speeding up their motor responding. And so a study I did, I'll explain this figure in a second, but I'll briefly explain the study first. And so a study I did looked at, well, what do speed emphasis instructions actually seem to manipulate with two models? Now, again, it's hard to tell. The selective influence bit's a bit tricky here, but this is more just to explain the model application, so I won't go too deep into that. Essentially, these graphs reflect the evidence for a specific model. Red represents so I did it through that. Yep, cool. Red represents a decrease in a parameter value. Blue represents the parameter values fixed, doesn't change over conditions, and green represents it increases. And so I have this for each parameter of interest: drift rate, so how good people are at the task; threshold, so how cautious people are; and non-decision time, how much time is dedicated to each type of process. And this is the change under speed emphasis. So for example, these red segments represent the evidence for with X being people and Y being the amount of evidence. So essentially, the more red you see, the more evidence for a decrease. And this is a decrease in drift rate under speed emphasis. So this would be people are getting worse at the task when they're put under speed instructions. In this case, red represents a decrease in caution, right? So people are getting less cautious under speed emphasis. And then in this case, red would represent a decrease in non-decision time. So people are just doing motor responses faster when put under speed emphasis. Does that make sense? Any questions, etc.?
Excuse me, could I ask to repeat this explanation about graphs? What represents in the red and blue and green again? Excuse me,
Cool, no problem. So red represents a decrease in the parameter value. So if it's under drift rate, that means it's a decrease in drift rate. Blue represents, and I should go to the other. Green represents an increase, right? So for drift rate, any red segments represent evidence that there's a drift rate gets lower, so people get worse at the task under speed emphasis. Any green segments in this plot represent the opposite. The drift rate increases under speed emphasis. So people get better at the task when put under speed pressure.
Actually,
and blue, yep.
I'm sorry, go ahead. I will ask you again.
Sorry, and blue segments represent no change. So people's task ability doesn't change when they're put under speed emphasis. Sorry, go
on. Thank you. So it means the less cautious is, the high accuracy is.
So this is more in terms of the model parameters itself, right? So the three main constructs of task ability, caution, and other processes.
So drift. that you stated before that the more cautious they are, the less they accurate, and the more we put them under pressure, they, for example, for fast training trials, you know, the more they get nervous, you know, distracted, you know, something like this. So maybe we should make a model for predicting the pressure and the you know, stress in these tasks, and then we're canceling out the fast, for example, fast tests and trials. I mean, we can canceling out the pressure effects.
Okay, so so this is a good point, but I think it's perhaps somewhat. So the focus here is just to essentially measure what's going on, right? So the focus here is just to understand. For threshold, it's just, do people get less cautious in the task? For drift rate, it's just to understand, do people lose ability at the task, so panic, feel under pressure when it's speed emphasis? I think your point goes even further, and it's then a why, right? So at the moment, it's just trying to figure out, does this happen? And it depends on the model used, which I'll get into in a minute. But I agree. I think you could go even further and then build a model that then goes, okay, well, if it does happen, when and why does it happen? So I think that's kind of what you're getting at, if I'm right. Exactly. Going a step further and building a model of when and why this happens.
Yeah, exactly. Thank you.
Yeah. Cool. So that's not quite what I'm doing here, but I agree. That's a good next step, and that's good stuff to be thinking about, because that extends these models even further. Thank you for the question, by the way. So getting back to this, so we've got, does drift rate decrease, stay the same, or increase? Same with threshold, same with non-decision time. And then I have this, oh, okay, the plot's failed, it seems. Regardless, I think this explains most of it. I don't know why my plots failed. That's weird. Essentially, that was just going to show that there's a difference between the diffusion model and the LBA, where the diffusion model shows kind of the opposite of this trend. Regardless, the key point here is that you can use these models to measure what's going on in the process and understand, well, I have this manipulation I'm interested in, speed emphasis. And then understand, well, does task ability change? Does threshold change? Does non-decision time change? So you've got some data and you want to know what's happening, what parts of the process may or may not be differing, and then using the models to see what does and doesn't differ. Does that make sense to everyone? The model application perspective? Cool. Okay, the second is model comparison. So model comparisons where you want to take multiple existing models and compare their relative ability to account for some data. So the reason for modeling here is that you want to quantitatively compare models and see which one best explains the data. I think this one's best explained through example, so I'll just get straight into the example. But essentially, you have different models that represent different theories of how the process operates, and you want to compare them in some precise quantitative way. So one example of this is the fixed versus collapsing thresholds debate. So what I've shown you before is something called fixed thresholds, where the amount of evidence needed to trigger a decision is constant over time. So it doesn't matter how long you spend on the task, on the decision, you will always require X units of evidence to trigger a decision and to respond. However, there's a different account, right? A collapsing thresholds account. And this account posits that perhaps people get less cautious over time. Perhaps when you spend more time on the task, you get more and more impatient, and you get more and more happy to make a decision based off less evidence, which will result in, at least in the model, your thresholds collapsing over time and doing this kind of pattern where you'll make a decision much more easily based off less evidence. So these are two separate theoretical accounts of how the process may operate, right? One is that You always require the same amount of evidence, no matter how long the decision goes on for. And the other being that you get more impatient over time and you're willing to settle for less when it comes to the amount of evidence required to make a decision. Cool. I guess the first question then becomes, well, what might motivate people to use a collapsing threshold, right? And there are several reasons that I won't get into too much, but based on optimality perspectives. One is that collapsing thresholds will always be able to, in almost every circumstance, be able to maximize reward rate, which is make you respond as efficiently as possible. So kind of getting back to what someone talked about before with, is there a kind of a best threshold to set? These thresholds will allow you to maximize efficiency even further than a fixed threshold under most circumstances. And they also help you avoid missing deadlines, because if you've got a deadline that's, let's say, here at maybe 5 seconds, you can collapse your thresholds before the deadline. You can collapse them right before the deadline and decide with very little evidence to avoid just completely missing the deadline and not responding. So again, these are two different theoretical perspectives of how the decision-making process may operate. And there's good reason for why people may actually adapt collapsing thresholds. However, although there's reasons why people might adopt collapsing thresholds, a question then becomes, well, do people actually seem to use them? Is it actually something that people seem to do? And the answer to this is kind of mixed from my findings, right? So this is an example of model comparison. Essentially, the plot is, and I think this kind of makes the point, hopefully, that there's some overlap between these categories of modeling. So these plots are very similar to the ones you just saw in model application that I talked about before. Except before they were looking at, does some parameter vary over conditions within a single model? You know, does drift rate decrease when you encourage people to go faster? Does threshold decrease when you encourage people to go faster? So on and so forth. Now these plots are comparing two different theoretical models, a collapsing thresholds model that has the collapse in it, or a fixed thresholds model that doesn't allow for that. And essentially you see a different pattern across studies. So if you tell people to maximize reward rate to be as efficient as possible, they still seem to mostly adopt fixed thresholds. If you give people a deadline, they instead seem to mostly adopt collapsing thresholds. And if you give people speed emphasis, which is a throwback to the previous study I talked about, then it seems to be mixed between fixed and collapsing thresholds. So again, hopefully this gives you an idea of what model comparison is. It's similar to what you do in model application, but rather than looking at do parameters differ between conditions, you're now quantitatively comparing different theoretical accounts of what's happening. Yep.
I have a question. We can change the parameters to achieve some explanation about our task. For example, you said here we can, instead of a constant boundaries, we can have some boundaries that change over time. But if we change the z parameters, for example, we have the participant have some bias. It may have some similar effect. I mean, increasing the z or decreasing the boundaries over time, they can have same effect on the RT. How do we account for this in our models, and how we explain it?
This is a good question. So one thing I should mention is that the collapsing thresholds account isn't over the experiment; it's over a single decision. I agree with your point, but I think your point's more so that as people spend longer on the task overall, so like on the first trial, they're less cautious, they're more cautious than on like the 500th trial, right? Which I agree with. But collapsing thresholds are a bit different. It's like if you've spent 2 seconds on a decision, you're going to be more cautious than if you spent 5 seconds on the decision. So that's a bit different. Two, you're absolutely right with your overall point that if you were to change thresholds, if you were to decrease the, if you were to change the thresholds over trials, it would have a similar effect to changing the starting point over trials. It's not exactly the same. It is separable, but they do have similar effects. In general, though, I should point out that for the most part, these are commonly referred to as sequential effects, and the models largely ignore sequential effects for the reason being that it's thought that these effects are kind of too minor. Oh, sorry. One, they're fairly minor compared to the bigger effects in the data, and two, incorporating them into the models make them so complex that they become essentially intractable and can't be used. Does that make sense?
Yes, completely. Thank you.
Cool, fantastic. I think someone else raised their hand.
Professor, in this case, can we view thresholds as synonymous to people's tolerance or level of patience staying at the phase of evidence accumulation, or their, let's say, hurriedness to rush to the decision making somehow?
Sorry, could you explain again?
I mean, you said thresholds are set for each individual per trial. Yes?
Yes and no. So theoretically, they could be set every trial, but it's assumed that it's largely constant over trials, and that each person has their own threshold, but their threshold they set is probably constant over trials.
So it is peculiar for each individual. If I
yes, yeah. I mean, so technically, the threshold of each individual probably does differ over trials, but it's generally assumed that the movement of threshold of over trials is probably sufficiently minor that it doesn't greatly affect things, and allowing for threshold to vary over trials would greatly increase the complexity of the model.
So with the increase in the complexity of the model, the thresholds may come down. Yeah. Or
yes, totally right. Oh yeah. So I agree. So I think this is something that like I've done before, but rather than letting thresholds vary over trials, I've let it vary over blocks. So block 1, block 2, block 3 of a task. And it definitely seems like people do decrease their thresholds over time to a point where they kind of settle on a threshold. So I agree. It definitely seems like over a whole task, people get a bit more impatient and will move their thresholds down. And I think in general, I think exploring this is a very interesting topic and something to build into the models. But generally it's not, usually people will just exclude early blocks of trials where they think people are still setting their thresholds and only look at the ones where they think it's fixed, because often they're interested in studying things other than this. And if you add too many components into the model, they become too complex and difficult to use, and they mimic each other, and they have parameter identifiability problems and all sorts of other issues. Does that make sense?
Yes. So overall, what I was trying to say was thresholds represents a behavioral indicator. I mean, just the time point where one participant makes the decision. So the signal below the threshold represents roughly the patience of the decision maker, or the tolerance of his or hers performing. Thank you.
Yes, agreed. Yeah. Yeah. Oh, cool. Yeah. Sorry. Yeah. Sorry. I didn't, sorry, I got mixed up there. I thought it was the question was a bit different than what you're asking, but yes, 100%. The area in between is kind of the patience. So yes, the patience decreases over time. Oh yes. Sorry. Hand, was there a hand, or was it down? No. Okay, cool. All right, sorry. So I'll move on. So hopefully this explains model comparison to you. Now we've had lots of questions, which is good, which means that I won't go through all the content at the end. So I'll probably talk about the last one, model evaluation, and then stop, because I think, Jamal, you want me done it in 10 minutes? Oh, shoot, that's yes. Cool. All right. So the last one is model evaluation, and I'll go through this one a bit quicker. And this is situations where we want to take existing models again and evaluate their ability to account for some pattern of data. So before, both in model application and model comparison, we were kind of talking about quantitatively assessing the models, right? So quantitatively assessing if the parameters differ, quantitatively assessing which of the theoretical models is better. Now this is more of a qualitative approach, right? We want to see, does the predictions of the model provide a good match to the pattern of data that we're seeing? So I'll go over this a bit more quickly than I would have otherwise. But we have some issues in the evidence accumulation model literature where models mimic each other and we get overly narrowly focused on RT and accuracy. Not a big thing for you to understand, I think, but this is just kind of the background of what I'm going to mention. But essentially, we've, as people talked about before, we've got this whole process, right? This whole noisy accumulating process, right? And we've got thresholds that govern when it triggers a response, but all we look at is this dot, right? Our entire focus in terms of data, like as brought up before, right? We're not using EEG to constrain this. We're not using eye tracking to constrain this. We're essentially only using the byproduct of the process to measure and to constrain these models, right? We're only using the time that people make a decision at and which choice they make to try and understand this whole entire process that's going on, right? Which seems a bit foolish in a way, right? It seems like we have insufficient data to gain a proper understanding of the decision-making process. You know, as people said before, it'd be great if we could better integrate EEG data, eye tracking data, et cetera, right? To get a more complete understanding of what's going on in the decision-making process. And yeah, so it seems like when we just use response time and choice, we have insufficient data to properly constrain our models and insufficient data to understand how things change over the course of a trial, how we change our minds, how strategy changes, all these kinds of things. So I think the best way to solve this is through more types of data. And I'm going to very briefly talk about a new type of data that I proposed in a paper, which is double responding. I mean, it's not new, but it's new to these models. And that's where you've got two options. And for example, you're doing a motion coherence task as usual, and the general motion is going towards the left, right? Except the first few sensory inputs, for some reason, you think you see motion going right. And because of this, you respond right. So you hit the key that corresponds to right, which in this case is slash. But then directly after your response, you see, oh, wait, there actually seems to be a lot of motion going leftwards. And so you go, oh no, I've made the wrong decision. This is terrible. And then you quickly hit the Z key directly after you've hit the slash key, right? This is something that I referred to as double responding. It's also been called error correcting responses. There's some old work by Rabbit on it. And they're just secondary responses that you make after the original response. Now, I've got lots of details here, but they're not the key importance that I want to talk about here. The key important bit that I want to talk about here is that you can then use them to extend and constrain the models, right? So after the standard process, you can assume that people keep accumulating evidence. And if the option that wasn't selected before then hits a threshold, this is an absolute framework, as you can see. If the one that wasn't selected before goes on and hits a threshold, then you make a second response, a double response. Now, there's a whole tree of models that I set up here that's not super important to the point, so I'll skip over it. I think this is actually kind of the main point of making clear what model evaluation is. And the key idea of what model evaluation is that you're looking at how well the data, which in this case are the dots. So green dots are correct responses, red dots are incorrect responses. And these dots to the side are the proportion of double responses. So proportion of double responses after correct responses, proportion of double responses after double responses after error responses. And the lines with crosses are the model predictions. And so this idea of model evaluation is assessing, well, how well do the data the dots, match the model predictions, the lines with crosses. And in this case, they don't match very well, right? There's a lot of what we call misfits. The models are predicting very specific patterns of data. The data, there's very specific patterns of data that the models aren't predicting well, right? These are CDF plots, they're a bit complex to interpret, but in general, just take my word for it, that the models are very much over predicting how skewed the distribution is, and how long responses are, and making people seem more accurate than they actually are. But the key thing to keep in mind here is that the crosses with lines and the dots don't match very well. So that shows a lot of misfit in the model. And then we can interpret where and why this misfit is happening. And so this is, I don't want to go into this too far because it will get quite complex. But this is the fits for one participant and another participant for a whole heap of different models. So that's the model that you saw before. And then these are a whole heap of different models. Now, I'm not going to go into what model's best and explain all that kind of stuff. The key focus, I think, for you is that there's a difference between these models, right? This model fits very poorly. This model fits better. These models down here probably seem to fit the best. These ones also show some misfit. This one shows a lot of misfit. And you can see that there's a difference between the models, right? You can evaluate which models seem to capture the data trends and which models don't. And so this gives you an idea of the fit and misfit of the different models, and allows you to evaluate where they successfully capture the data and where they don't. So these models do poorly, as I said, these models do better, and these models do the best. So not important what the models are for, I think, your learning at the moment, but the main point being that you can see these differences between models and their ability to fit data. The last thing I'll very briefly mention, then I'll tune out for question time. I won't go into the pitfalls type stuff, but I'll put my slides up if you ever want to look through them, is model development. And I've already kind of talked about this throughout, right? Model developments where you want to take an existing model and extend it, or develop a completely new model from scratch, right? And the purpose of this is to make a new model that we then use for model application or model comparison or model evaluation, right? So we're creating a new model that we can then use to measure parameters, or as a theory in a quantitative comparison, or as a theory in a qualitative comparison. And the reason I'm not going to go into this too much here is that I've already kind of covered it beforehand, right? Like the collapsing thresholds model was a model that was developed to represent decreasing caution over time. The double responding model that I mentioned was an extension that we made to account for double responses and further constrain the models, right? So essentially model development, I always feel the need to mention because it's the most integral part of modeling. It's how we create our models, but it's not really a specific, to actually use the model, you've got to use one of the other categories, if that makes sense. Now I had a lot of other stuff on like pitfalls and stuff, but I'm kind of at time now. So I think, Jamal, correct me if you disagree. Oh, wait, how long do I have? 10 minutes. Oh, I have 10 minutes from now. Fantastic. I'll continue then. But please do stop me for questions if you have them. Thank you for letting me know, Jamal. All right. So now I'm going to mention now are some pitfalls of evidence accumulation models. So we've talked about model application, comparison, evaluation, development. But I've kind of just been all rosy about them, right? And how good they are. There's also pitfalls of using evidence accumulation models in these contexts. And while they can be useful, there's also things that you want to try and avoid, right? Although I very much want to encourage you to use them and get to know them and take full advantage of today on the workshop, there's things to keep in mind when you're using them that can go wrong and that can make your inferences potentially misleading. And each category has its own unique pitfalls. I'll focus mostly on model application because I think that's what you're most likely going to be doing with the models. That's what most people do when they start out using them. But as I said, I can also send people my slides if they want to see the other things I would mention. So to me, when we're doing model application, the most important and underappreciated limitation is something called parameter identifiability. Now, parameter identifiability is the ability to correctly and reliably identify the parameters that we're estimating. Essentially, this works under the idea that there's some true data generating process. There's some model that actually generated the data we're seeing, some cognitive model that actually generated the data. And we want to be able to identify, if we're using the true model, what parameters generated these data. That's a bit complex, I guess, a way to explain it. But I think the most simple way is we want to know that if we were to generate data with this model and these parameters, that we would be able to get that back if we were to estimate the model to the data. It's essentially it's essentially the reliability of estimating these parameters, if you know about reliability. Does that make sense? Anyone have any questions? Cool, I'll move on then. All right, so one of the models I mentioned before, the LBA, has a bit of an issue with this. And it also is a bit more general, as I'll mention briefly after this. Now, these are scatter plots with like 8,000 data points. The x-axis represents the data generating values. So you simulate some data with the model with certain parameter values. The x-axis represents these parameter values. The y-axis represents then you take the model and estimate it to this data that you simulated and see what parameter value you get back when you estimate the model to the data that it generated. So the red line is the line of perfect recovery, which means that if everything were to fall along the red line, that would mean that you generated data from the model with this parameter value. And when you estimated the model, you got that exact parameter value back. So essentially perfect reliability. Any deviations from that red line become problematic, and high deviations from the red line become extremely problematic to the point of the parameters being unidentifiable. So essentially the key takeaway here is you can probably mostly infer it from the correlations, but the drift rates, which I'll focus on VDiff, is very well recovered, right? As you see, I've put a green box around this because it's very well recovered. It's very well identified. You can reliably estimate the drift rate. However, the estimation of threshold isn't very reliable in the LBA. Again, it's just one of the absolute evidence accumulation models. You get this issue where there's a big range of different parameter value. If you were to generate with a parameter value of 0, you could estimate anywhere between 1 and -1. There's a big range of potential parameter values that you could estimate. So the estimation of threshold is very unreliable in the LBA. And non-decision time is kind of on the fence, right? It's not as good as drift rate, but it's much better than threshold, but there's still quite a bit of variation in the values you could estimate from a generating value. This is kind of opposed to the diffusion model, which shows very high correlation and robust estimation for drift rates, thresholds, and sorry, I've called threshold B here. That's a different terminology, but also one that people use. For drift rates, threshold, and non-decision time, the estimation is reliable across the board for the diffusion model, right? So there seems to be an identifiability issue in absolute, and here are some other models. They're all absolute evidence accumulation models, and they all show this same issue, right? Threshold seems to show unreliable estimation. So there seems to be a general issue for these absolute evidence models, these accumulator models, not the diffusion models, the accumulator models, where they have some parameter identifiability issue in getting a threshold, right? And although it differs, this qualitative issue is always there, right? But like anything, there are solutions to this problem, right? For me, the answer, as it has been in many cases, is constraint. We need to well constrain the models. Now, although when we're doing model application, we want to allow maximal flexibility, this can sometimes destroy the measurement properties of the model. And this is the case with the LBA and these other absolute accumulation models and thresholds. If you allow them to be as flexible as possible, it destroys their measurement properties, and you can't reliably estimate threshold anymore. You can't reliably estimate caution anymore. However, constraint fixes this. Now, I put, this is the LBA from before. As you can see, threshold is poor. Now, if I constrain something in the model, which is this V mean thing, I won't talk about what it is in detail. But if I add a constraint to the model, I can fix this problematic measurement property, right? All of a sudden, drift rate's still good and non-decision time's better. And now threshold is substantially improved, right? Threshold's no longer unidentifiable. It's not as good as in the diffusion model, but it can be properly identified now. And this is the case across all the models. So all the models I showed you before, adding this same constraint can fix the properties. The key point I'm trying to make here isn't that the LBA or absolute evidence accumulation models are bad. The point is that if you don't check things like the measurement properties of your model, you can run into issues in model application. If you don't check that the estimation is reliable and robust, then you can end up with a model that doesn't have reliable estimation and then make poor inferences based on this unreliable estimation. Now, this can almost always be solved with further constraining the model, right? The only issue is that you've got to make sure you know the measurement properties of the model and you understand what's going on beforehand, right? So run things like these recovery studies, etc. So I guess the two key takeaway points from this bit is that using these models for model application is great and can tell you so much more about your data than standard RT and choice. But you've got to be careful about things like parameter identifiability and how reliable the estimates are in this context. And you've got to test these things and make sure they are reliable for your context. Otherwise, you can have misleading inferences. So although it may seem easy to do, there can be more complexities to this. Yeah, sorry, raised hands?
Actually, I have a question that,
cool.
What was those, constraints in particular, could you please go a little bit?
Oh, what the constraint is? Okay, yeah. So essentially, in these absolute evidence accumulation models, they have a drift rate difference because they've got two separate accumulators, right, that are independent. And so there's a difference between them, and there's an overall kind of average value, right?
Yeah.
And the difference is what we're interested in, right? That's task difficulty. The average is just kind of meaningless and it isn't even present in the diffusion model, right? And so if we fix this and constrain this in some way, then it fixes the identifiability issue.
So what I mean is, what are those constraints, ingredient? I mean, what are those elements for constraining a model? I mean.
Oh, as in, like when would you constrain it or how would you constrain it?
How would you constrain?
So how would it? Usually you pick a parameter. Usually you pick a parameter that you're not interested in and that you don't think will vary across experimental conditions and groups, and fix it to have the same value across conditions. So essentially what you want to do is you want to fix parameter. You want to try and fix as many parameters as you can to have either constant values, which is not as good because it's a bit over constraining, or fix them to take the same values across multiple conditions where you're measuring differences in other parameters. So essentially it's all about fixing parameter creating less freedom in the model by fixing parameter values. Does that make sense?
Yes, exactly. Thank you.
Cool. No problem. Thank you for asking that question. I didn't realize that I didn't quite get that out properly. All right. So I think this concludes the main part of the talk. I've also used my 10 minutes. Do you want to take over now, Jamal?
You can continue, Nathan.
Oh, I can continue. Are you sure? Oh, no problem.
Yeah, sure.
All right. Okay, cool. So I'll just be very brief on these ones then. So model comparison, there's also some pitfalls to model comparison and model evaluation too, right? So model comparison may seem objective, but the conclusions can be completely dependent on the choice of the quantitative method you choose, right? So you've got to choose some, if you're going to quantitatively compare these models, you've got to choose some metric to do it by, right? Some quantitative measure that says this model's better than this model. But the conclusions of your study can completely depend on your choice, which one you choose to use. And this is by design. Each method tries to select a model based on different criteria, but this is something you need to keep in mind, right? You can't just mindlessly choose AIC or BIC or any of these selection criteria at random, right? You've got to think about your choice, because your choice can matter and change the conclusions that you make. All right, so this is a quick plot, and I'm not going to go into too much detail. I'll actually just skip ahead here. But essentially, this is the correlation between the different metrics and their decisions about empirical data, whether there's essentially the correlation between metrics and what model that they chose. So green represents very high agreement, red represents very low agreement, and black is in the middle. So if these models were to be perfectly agreeable, like they are in this situation, so they are in some situations, here there's perfect agreement. But that's what we expect it to look like if there's perfect agreement. However, there are some situations, this is essentially where there's small effects. I don't want to get into it too much because there are probably many situations where it's like this. But these different methods can disagree, right? So again, sorry, we've got a different method here and a different method here for each thing. And as you can see, there can be some big disagreement, right? Particularly between DIC, WIC, AIC, and BIC, bridge sampling, and thermodynamic integration. So essentially, the key takeaway point here is that that these methods are showing large amounts of disagreement on what model they're selecting. One method selecting this model and another method selecting this model, and they're doing it consistently. So they're consistently disagreeing within this context. The specific context isn't important, I think, for the time being, but the important factor is there are contexts where different model selection methods, different metrics that you calculate to decide which model's best, can completely disagree with one another, and therefore can drive your conclusions. So an oversimplified explanation of why they disagree is that cross-validation punishes models for overfitting to a sample of data. These are things like AIC, DIC, WASC, LUCV, if you know of them, perhaps you don't. But they punish based on overfitting, right? And the Bayesian model selection methods, things like BIC Bayes factors, punish for models having spread out predictions, being able to predict a lot of data. Essentially, all this means is that as you collect more and more data, there'll be less and less noise in the sample of data, so there'll be less and less overfitting. And so cross-validation will view models as being more similar and there being less difference. Whereas Bayes factors will still show differences between them because of the prior predictions, the spread out prior predictions. To go even simpler than this, cross-validation favors more complex models. So cross-validation is going to, on average, select a more complex model than Bayes factors that generally prefer simpler models. So that's a real oversimplified explanation, but hopefully that gives you an idea of why these different methods differ. And so although model comparison is ideal for quantitatively comparing models on available data, the choice of how you compare them, what metric you use, is really important. And so you need to consider and justify that. The very last one's model evaluation. And so as I kind of showed before, it's the key to understanding what trends a model can and can't capture in data, right? What trends it can and can't explain. However, assessing whether a model is doing good or poorly, or which model is doing better, is very tricky because it really depends on what aspects of the data you look at. Now, as a quick example, I've got 3 panels here. One is the empirical data. One is the DDM, which is the diffusion model. And one is the UGM, which is something called the urgency gating model. Now, the models themselves aren't super important for this example. It's just looking at how well they match the data. And as you can see, the diffusion model provides an all right match of the data. You know, these things seem to be similar. You know, there seems to be a similar kind of pattern in the data on the left and the model in the middle. But the urgency gating model seems to match better, right? It seems to more closely match what's happening in the data than the diffusion model. So by this plot, it looks like the urgency gating model is doing better. And then we have a second data trend we can look at, right? Again, not super important what it is for the purpose of this talk. But here's the data here, and here's the diffusion model prediction, and here's the urgency gating model prediction. And in general, although the diffusion model is kind of close, it does seem that the pattern, you know, the steep decline does seem to be more closely matched by the urgency gating model. So again, this pattern again seems to suggest the urgency gating model is better. However, if we go to this third pattern, and I'll bring it up closely, we've got, it's similar to the plot I showed you a while ago, the CDF plot, where the triangles are the data, the solid lines are the diffusion model, and these are dotted, like jagged, dotted, whatever you want to call them, lines of the urgency gating model. The diffusion model provides a substantially better account of these data. So as you can see, the solid lines quite closely match the triangles, whereas these dashed lines are way off the triangles, right? So my key point here is that we've got three different patterns of data that kind of tell three different stories about what model is best. So although this is very useful in understanding where models fail and where models do well, you can get caught when you try and use it to compare models, you can get caught in this problematic situation where it's difficult to know, it's difficult to know what patterns of data you should look at. And if you only look at some and not others, you may get an incomplete picture of what's going on. Cool. So that kind of sums up what I said. It's necessary, but it can be dependent on the trends. So the take-home message are essentially these, I think evidence accumulation models are very useful, right? And they can tell us so much about data and can give us a much deeper understanding of what's going on at a process level through model application. So they can tell us a lot more about our data than just looking at response time and choice scan. And they can also improve our overall understanding of human decision-making, right? They can also be used in model comparison and model evaluation to much better understand the decision-making process as well, like I showed you with collapsing thresholds and with the double responding stuff. However, there's limitations as well, right? They're not a magic wand. You can't just wave them at everything. You've got to be careful of certain things, right? And while you can avoid many of the limitations and the pitfalls, you have to keep them in mind, because if you don't keep them in mind, you can fall into one of the pitfalls, right? And you need to think carefully about your choices. When you're doing model application, you need to think carefully about the measurement properties of the model and whether they're reliable. When you're doing model comparison, you need to think carefully about what model selection metric you're picking. And when you're doing model evaluation, you've got to think carefully about what data trends you're going to look at. If you keep all these things in mind when you're using evidence accumulation models, I think you'll do a great job using them and you'll be able to do great research using them. But it's important to keep them in mind, otherwise mistakes can be made and incorrect conclusions can happen. I hope this was useful for everyone. That's everything. Thank you for letting me talk for so long, Jamal. And thank you for your time, and please go on.
Nathan, many thanks for your great presentation.
No problem.
We really appreciate it. You really opened the matters very good and made my job easier for the next hour.
No problem. I'm glad to help.
I can easily go into the mathematical details of the model.
Okay, oh, good. That's good. I'm glad that's where the next step you're going is, because that's where I was hopefully leading to. All right, fantastic. Should I wait for questions or should I head off now?
Yeah. Everybody, any questions?
Oh, yep, cool.
Hello. Thank you for your lovely, I'm sorry, for your lovely lecture. Actually I have a question. I have two questions, in particular. First is, we have two, as I get it, there are two types of model evaluation, two types of, in better words, getting more accuracy. The first is mathematical, optimization. For example, you construct a model and then you try to optimize the model from those empirical data you get and the and the tests you created. But my question and my focus is about how you could be how could you be sure about the actual and the first phase that was testing, creating a good test, which creates the best model. How could you be sure about the actual test as itself, psychological test?
That's an excellent question, right? Because as far as I'm concerned, you can't ever be sure, right? There's always doubts, there's always uncertainty. That's why we haven't solved psychology yet. I think if there was no uncertainty, you know, we would all be out of jobs because psychology as a science would be solved. So I don't think you can ever be certain, right? I think the key thing is that you I think the key way to combat this uncertainty is to be as comprehensive as possible. So rather than just doing a single test or developing a model in a single way, you try and do it as many ways as possible, right? You try and come up with lots of tests and lots of potential extensions of the model, and lots of potential explanations, and try and do all of these tests, right? And see when you cover all of this space, all of these tests with all of these models, what seems to come out on top. Now, obviously that's not perfect and it's always prone to error like anything is, but I think the more tests you do and the more models you consider, the more certain you can become that at least something you did was right.
And thank you. And the second is, as we know in psychology, we have some sort of, subliminal stimulus, and those, that we are not conscious about our, actual behavior. For example, whenever you are in the test, psychological test, like the one you've been through, there are millions of variables are affecting, the vast variety of variables are affecting on your choice. And actually using the same method would miss some higher dimensional data in some sort of psychological view. I would like to know, has anyone done anything regarding to subliminal stimulus and those unconscious experiences of those kind of things?
Excellent question. So I wouldn't this can become tough because it depends how exactly you define subliminal stimuli, but people have done, so there's lots of kind of cueing paradigms where you cue people to look in one direction or the other, or cue them with what the stimulus will be before it happens. But you present it so fast that they don't realize they're consciously perceiving it, right? So you present them with a cue, but you take it away really quickly. And if you were to ask them, did they see a cue? They would say, no, I didn't see a cue, right? So it's too fast for them to consciously perceive it, but you still do see differences based on these cues, right? I'm not sure how well this has been explored with evidence accumulation models itself. So this could actually be a good topic for future research, because I don't think evidence accumulation models have been used for it. But this is certainly explored with choice response time tasks with queuing. And I think it would definitely be a good area to apply these models to.
For example, you shown on your slides,
yeah.
two sorts of, of testing, double.
Yes.
Yes, I can't recall the exact name, but maybe we can create a test with, for example, those directions of darts, and the flow of darts, and recognizing those flow, and then we use some sort of really tiny frames of different pictures, different statements, like you're gonna lose, and then in other group we might using really fast frames, like motivative statement, like it's gonna be work out, something like this. And then we organize the model and using the same exact model, and then we cancel out the existing model and its outcomes, and then we can find out, does this subliminal stimulus done anything and has any effect on this particular example or not?
Okay, fantastic. So thank you for clarifying. One, that as far as I'm aware, that hasn't been done before. And two, that's kind of a textbook model application question, right? So I think it would be a great question to ask, right? Where you could have these two conditions where in some blocks or to some groups of people, you present different subliminal messages, and then you see, well, does telling people they suck subliminally, does that make them worse at the task?
Exactly.
And yeah, you could totally apply the models and see if drift rate changes and measure all this. So yeah, that would be a textbook model application study for sure. But as far as I'm aware, it hasn't been done. So don't worry, I won't tell anyone about your idea.
Thank you so much.
No
I
problem.
appreciate it.
I think there's another hand up. Sorry, Jamal, please do cut me off if you need to
I
at some
think
point.
Alireza has a question.
Yeah,
Yep.
thank you, Mr. Amani. Can we account for some effective, let's say, states of the participants in our experiments, like mood or like, the overall psychophysiological states they're in?
So this is a
And-
good, oh, sorry, go on.
Yes, that's all. For example, anxiety, for example, I don't know.
Cool. So
Pessimism.
yes, you can, but it's not done very often. So I have a study where it's not quite what you described, but you could do it using a similar methodology where we measured this construct known as need for closure. So it's people's kind of intrinsic desire to get closure, to get certainty about something, right? And looked at how that related to decision thresholds, so caution, and then assessed how closely these two parameters related to one another and found that there was some relation between them, right? Now, sometimes people do incorporate, I think this gets, please correct me if I'm wrong, but I think this gets along with what you're saying. You can look at how people's states, so whether it be a long-term state like need for closure or a short-term state, perhaps like their general anxiety of being in an experiment room, and see how this relates to different parameters in the model, right? So you could definitely do this. And I could totally imagine there being a relation, right? Like I could imagine those who are more anxious perhaps being worse at the task, so having lower drift rates because, they feel under pressure, right? Or those being anxious also having lower thresholds because they're nervous and want to get it over with. So is that what you were getting at? Because I think, yes, it's definitely a possibility, but something that's not done super often. Sorry, did that answer your question?
Yes, roughly. So you mean there isn't a big amount of literature on it, huh? Yet.
So there's definitely literature using psychophysics and evidence accumulation models together, but not quite in the same way that you're talking about. So usually it will be like you do an eye tracking study and then you try and incorporate eye tracking into the model, similar with how I did things with double responding, right? But it's more rare that people will try and measure things like anxiety or those kind of things during a study and incorporate those. Usually if it's measurements that people incorporate, it's like EEG or eye tracking or kind of these more, I guess, objective measurements, should say. Does that make sense?
Almost, yes.
Okay.
Thank you.
All right, cool.
Okay, I think Arash has a question. Arash, please.
All right, fantastic.
Thank you. I have a question. It may be a little off topic, but was there any attempt to use these models to mimic human behavior? I mean, they are very good in understanding how we make decisions and predict some data, but is there a way that we use this model to mimic our behavior in AI or, I don't know, robotics? We can't make this, it's just a guess, we can't make a complete model. We mimic them, but we can use them as an evaluation how well AI can mimic human. Is there any attempt in this?
So not particularly, but I think it's a good idea and something that I've thought about before. Now, obviously the issue is that this only handles the middle cognitive part, right? You'd need something that encoded the information in the environment and then output responses, right? So this would be an incomplete process, right? But I think if you were trying to use an AI to make decisions, then having this model in the middle could definitely be useful, right? And if you were to have something that took in the information, how do I put this? I think usually AIs are almost the opposite at the moment, right? They take in information, output responses, but don't have this complex decision-making in the middle. It's usually like a neural net or something like this, right? But I think if you would actually have a model of decision-making in the middle, it could be very useful, right? And yes, I agree. I think I think it could be useful, and I think you could turn these into complete models of what people are doing and trying to mimic human behavior. But as far as I'm aware, it's a fairly untapped or almost completely untapped area so far. But it's definitely an interesting avenue for using the models.
Thank you very much.
No problem.
Okay, Nathan, many thanks again for everything. I really appreciate it.
No problem. Thank you so much for having me. Should I head off now so you can, sorry?
Yeah.
Should I head off now so that you can move on?
I think we have another question.
Oh, wait, sorry.
Sorry.
Sorry. Thank you
Yeah.
for your good lecture. This lecture gives me a bit intentions. Apparently, seeing we are frequently believing in desire and limitations. I have two questions. Limitation and bounded having a good effect on concentration in short time?
Sorry, could you please re-ask?
Limitation or bounded in decision making. Having good effect in concentration short time.
Yes, I guess this is an interesting point. I think these models don't usually consider so much about concentration, right? So I think they generally assume that concentration is either fixed over time or that it varies over time, but varies in a reasonable amount and in a non-systematic way. So the models generally assume that either people concentrate equally well or they just have random focus on trial to trial. But I think my opinion would be that concentration probably decreases over time. But this isn't something that's really incorporated into the models usually. Is that what you meant?
Not exactly.
Okay.
Sorry. Thank you so much.
Sorry, no problem.
Okay, thanks. Nathan, I think we can finish the meeting.
No problem, no problem. Fantastic. Thank you so much for having me. I'm very glad to have been here, and best of luck with the rest of the workshop, everyone.
Thank you so much.
All right, fantastic.
Have
All
a
right.
nice day. Bye.
See you, you too.